Assalamu alaikum. Welcome to Digital Communications online lecture. I hope you guys are all fine and in the best of your health. I'm looking forward to receiving many questions in the interactive session, so please utilize the session that I've announced this week, and make sure that you all attend the interactive sessions. Please also download the PDFs of my lectures from the Canvas, so that when you listen to my video lectures, you have those PDFs available to you and you may write notes on those PDFs. So today we are going to talk about a new topic called vector and signal space basis functions using Gram-Schmidt orthogonalization process. Before we move on to that topic, I would like to review what we have done in the last time. We covered an important topic that involves the derivation of the matched filter, which is a receiving filter that tries to maximize the signal component compared to the noise component at the output of that filter. The scenario we consider is very simple. We only consider the received signal in the presence of AWG and noise without any other external factors from the channel. So we assume that we have a very nice ideal channel in which there are no interference elements present, only the noise is present in the channel, and the noise is added onto our transmitted signal SI of t. I stands for the ith transmitted waveform. We assume we have so many waveforms and the ith one was transmitted at one given time. So R of t is received and transmitted signal will have the impact from the noise in additive form. So R of t is nothing but the transmitted signal and the noise added on top of it. Then we have the receiving filter, which we derived in the last lecture, that will have the maximum signal component compared to the noise component at the output of that filter. Then we sample that output at t is equivalent to capital T, like every symbol time duration we sample it to get one test statistic out of that symbol period. Now, given that test statistic, we would like to compare it with some threshold gamma. Whether that test statistic is greater than gamma, we would take the decision in favor of one of the hypotheses, and other hypothesis if it is less than this threshold gamma. So this is what we did last time, and we did some derivation, and we tried to realize the mathematical equations out of that model, and we came up with a very nice conclusion that the impulse response of the match filter H of t is nothing but the shifted and flipped version of the signal itself. Assume small k is constant, which is equivalent to, say, for the sake of simplicity, it is assumed to be, say, 1. So you only have the flipped and shifted version of the signal copy itself as a impulse response of the match filter. In other words, the filter that we have here is nothing but SI of capital T minus small t, right? So if we have, say, 10 signal copies here at the receiver end, by the way, this is the positive sign, like I corrected it last time. So suppose we have 10 signal copies here, 10 possible signal copies here to be sent from the transmitter end. We would require 10 match filters at the receiver end respectively. Each of those match filter will be placed against one of the copies of the transmitted signal. So we have 10 branches of the match filters at the receiver end for each 10 possible copies that could have been sent from the transmitter end. right? So if we have, say, 32 possible signals, then we would have 32 match filters in as a result. There would be matching, that would be matched against those possible copies. So this means we have a scenario in which the complexity of the receiver block may increase with the number of possibilities at the transmitter end. So somehow we need to reduce this complexity, and today's lecture is all about it, how we can reduce the complexity of the receiver structure so that we may not need so many match filters at the receiver end. Somehow we need to reduce the number of match filters at the receiver end to reduce the complexity of the receiver. So this is what we are, this is the context in which we are going to study a new topic today. Alright, so next I would like to see how we can reduce the complexity of the match filter, which is a very important topic because we have seen that match filters, the number of match filters depend on the number of possible signal types that you may have from the transmitter end. So if you have, say, 32 possible signal types in a digital system, then you would require 32 possible match filters branches at the receiver end. The received signal would be compared with all of the possible impulse response and sampled at t is equivalent to capital T and later on be compared with thresholds to give you the final decision, right? Something like that. Right, so now let's see how we can reduce the possible signal set in a digital communication system using basis functions such that the complexity of the receiver structure could be reduced. Just a second. Right, so before we start a Gram-Schmidt orthogonalization process that is going to help us determine the basis functions for a given signal set, we need to recall the signal space, the properties of that are associated with the basis functions, and then we will move on to the Gram-Schmidt orthogonalization process. And of course we are going to do several examples to help you understand how we calculate the basis functions given the signal set. So now we are clear that we have a problem that we have a certain number of signals to be represented using a reduced number of basis functions, so that the requirement of number of match filters at the receiver end could be reduced somehow. So let's start. This is a view of signals, orthonormal signals basically. Assume we have orthogonal signals and we would like to check their correlation with each other. If the two signals, say these two signals, psi I of t and psi j of t, if these two signals are orthogonal to each other, then they are totally independent of each other and will have no correlation with each other. Their multiplication and integral over the orthogonality period will give you the result 0 when the signals are different, that is when I is not equivalent to j. And when the two signals are same, that is when I is equivalent to j. So this is equivalent to as if you are comparing one of the signal with itself, correlating the signal with itself, and it will give you the maximum result. The maximum here is 1. Why? Because the result is normalized with the under root of their energies. So that's why we call them orthonormal signals. not orthogonal, but orthonormal signals. So we have a signal set which is orthonormal in nature and described by this property. This is 1 when the two signals are alike, and this is 0 when the two signals are different. So the basis functions are orthonormal functions that obey this property, that follow these rules, right? So we need to come up with a set of basis functions for the representation of our signal set that we are going to use for transmitter and receiver. That is, we would like to represent our signal in terms of these basis functions. Assume we have capital M signals. I varies from 1 till capital M. So we have say ith as I of t, which is ith signal, transmitted signal, represented in terms of the basis functions, n basis functions, capital N basis functions, and each basis function will have its contribution towards the signal as I of t. Just like you represent a vector in using its orthogonal components x, y, and z, and along with their contributions that tell you how much of x component or y component or z component is present in a vector. The same way you can represent any signal in terms of orthonormal basis functions along with their contributions that indicate how much of the orthonormal function contributes towards the original signal Si of t. So normally we have capital N which is less than n equivalent to capital M. That is, the number of basis functions capital N are always less than and equivalent to the possible signal types M, right? So assume we have 32 possible signal times M and we end up getting only 4 basis functions, that is capital N is equivalent to 4. So we would be representing all the possible 32 signals in terms of the 4 possible basis functions, right, using 4 possible basis functions. So this means the match filter may not need to have 32 branches at the receiver end to match with. It only requires to have 4 branches against 4 possible basis functions. So your complexity will reduce significantly if you represent your transmitted signals in terms of the basis functions, right? So the contribution basically creates the difference, and it will uniquely, each contribution will uniquely contribute towards the particular signal type. Depending upon the amount of contribution, you would be able to differentiate one signal from the other signal, right? And how do you compute the contribution AI of j? AI of j is nothing but the multiplication of the original signal Si of t with the basis function out of which you would like to calculate the contribution from, and integrate it over the orthogonality period 0 till capital T. So that's how you calculate the value of the contribution. If you recall Fourier series, we did a similar analysis there. Instead of these functions there, we had sinusoidal periodic complex exponentials or sinusoidal functions along with their corresponding coefficients, right? So it's like you have coefficients here and the orthonormal basis functions there again to represent your signal, right? So it's expansion of any signal Si of t using orthonormal basis functions to reduce the complexity of a match filter. Now, given the set of functions Si of t, you would like to find out the psi j's of t. Like, how do you find these basis functions out of the given set? This is what we would be talking about shortly, And Gram-Schmidt orthogonalization process will help you to calculate these basis functions out of the given signal set. How do you represent these signals in the end if you have, say, calculated the basis functions for a given signal set? How do you represent them? You use the constellation diagram. This picture there is having two basis functions, phi1 and phi2. These are the two basis functions. Assume you have calculated these basis functions out of the GSO process, and you had three signals to represent using the basis functions. Now S1 of t will be equivalent to 3 times phi1 of t plus 1 times phi2 of t. Similarly, S3 of t will be equivalent to 2 times phi1 of t and minus 2 times phi2 of t, right? So you can represent these signals, three signals, using the two basis functions. This is just an example in which I show you the representation of the signals using the basis functions using constellation diagram, right? So these are the constellation points S1, S2 and S3. The constellation diagram has the basis functions on each axis, and each axis, basically orthogonal axis, represent a particular basis function. These axes are orthogonal to each other, they are mutually independent. You may have the third axis if you had another basis functions, phi3. Then you would have three-dimensional representation of the constellation diagram. Difficult to visualize, of course. But you can use MATLAB or any other software to plot the results on a constellation diagram. If you would like to calculate the energy of a signal using the basis functions representation, you may substitute Si of t equivalent to Ai of t, Aij of t times psi of j of t, and summation over all the basis functions and the contributions. Take the square of the whole term and integrate to get the energy of the signal. We just substituted this term Si of t in that term in this equation there to calculate this term there. Right, so it all boils down to the contributions. The total energy will be equivalent to the sum of the individual contributions. The formula states that the total energy of the ith signal will be equivalent to the sum of the contributions that it had using the basis functions, using the n basis functions, right? So in summary, we have, say, these properties that are valid for the analysis. The inner product or the dot product is defined using this mathematical operation in which we multiply the two signals together and integrate over the orthogonal period to get the result. If you would like to calculate the norm of the signal, and then it's nothing but the under root of the energy. Norm square, represented like this, is equivalent to the energy, and norm is equivalent to the under root of the energy. Okay. Orthonormal property is nothing but, like I've already discussed, when you have two different signals, then the area under the curve of them will be 0, or in other words, the two signals will have 0 correlation with each other if the two signals are different. When they are same, that will be equivalent to the maximum value, which is equivalent to 1. Or if they are not normalized, then it will be equivalent to the energy of the signal, right? Next, we see how we can obtain the possible basis functions given the set of transmitted signal possibilities. right? So GSO process is going to tell us how we can obtain the basis function phi's out of the given possibilities of signal set SIs. I've included all the steps here in the slides for you. Let's see how we can compute the basis functions out of the GSO process. The step 1 of GSO process is to choose phi1 of t equivalent to S1 of t normalized by norm of S1 of t, where S1 of t can be any function chosen out of the given possibilities. You could have selected S2 of t here, or S3 of t here, or S4 of t here, assuming you have 4 possible signals. But provided the signal is not equivalent to 0, you could have chosen any signal as the first signal and normalize it by its energy to get the first basis function. This is the first step, which is very simple. That is, you select one of the signal type S of t out of the possibilities, provided that signal type is not equivalent to 0, and normalize that result with its energy, norm of its own energy, norm of the signal, sorry, and get the first basis function out of it. You can calculate the energy of the first function easily using this formula there, right? And substitute the under root of that energy E1 there in this function, right? So in the end, S1 of t can be represented in terms of the basis function phi1 of t. If you substitute under root E1 on the left hand side, so S1 of t is nothing but under root E1 times phi1 of t. That is, S1 of t is represented in terms of the basis function phi1 of t, where S11 is basically calculated as the under root of E1. How? If you use this formula there to calculate S11, it is nothing but S1 of t times the first basis function phi1 of t. And you chose phi1 of t as S1 of t divided by under root E1. So if you substitute the formula there, you end up getting S1 of t times S1 of t, and integrated over the orthogonality period 0 till t. This will be equivalent to energy of the signal E1 divided by under root of E1. E1 divided by under root of E1 will give you under root E1 in the numerator, right? So you can calculate them on a piece of a paper very easily. These are very simple and self-explanatory mathematical steps. S11 will be calculated as under root E1 out of that operation, out of this signal, right? So in the first step, we have calculated the basis function very easily out of that process, which is nothing but the normalized version of the chosen signal out of the possible signal types. The second function, let f2 of t be the second function, and it is nothing but subtracting the contribution of s2 of t onto the basis function phi1 of t from the function s2 of t itself. That is, you choose the function s2 of t out of the available remaining functions minus the contribution of s2 of t using the previously calculated basis function phi1 of t. That is, you are removing the portions of the signal which are correlated to previous basis functions from the signal s2 of t. You subtract the contributions of s2 of t using the previously calculated basis function from the chosen s2 of t function in the next step. The resultant function is stored in f2 of t, and you normalize that result with its energy, right? And there you get the second basis function, which is totally independent of the first basis function. The second basis function will be orthonormal to first basis function phi 1 of t, right? Then you repeat the same step and procedure until all the basis functions are found. That is when, suppose you have this fk of t in one of the steps equivalent to 0 as a result, you will stop the process. And if you have tried and tested all the possibilities that are remaining in the signal set, then you stop the process there, and whatever the basis functions you have calculated with, in the previous steps will be your finalized set of basis functions. I know it's difficult to understand it in one go unless I do an example for you. In the next few slides, you will see the worked out examples in a very simple manner to make you understand how to obtain the basis functions out of the given possibilities of the signals. Right? Now let's go to the examples, and then you might need to come back to this slide again to better understand what's happening. Alright? So let me repeat the summary, and then we will go for the examples. The first basis function is the normalized version of the first signal itself. That is the step 1. The first basis function phi 1 of t is the normalized version of the first signal that you have chosen. This may not be s1 of t. That depends what is the first function that you have chosen in the given step. In this slide, the author has chosen s1 of t as the first signal. You may have chosen s2 of t there and normalize it with e of under root e2 to get the first basis function, right? That is phi 1 of t equivalent to 1 over under root e2 times s2 of t. You could have chosen s2 of t, right? So it's chosen arbitrarily, provided that signal is not equivalent to 0. So in summary, the first basis function is the normalized version of the first signal chosen by you. The successive basis functions are found by removing portions of the signals that are correlated to previous basis functions and finally normalizing the result. That is, the second basis function is done in the second step here. It is found by subtracting the portions of the function that are mapped onto the previous basis function. That is, you are removing the contributions of s2 of t that are correlated with the previous basis function from the original function itself. So the remaining portion will be stored in f2 of t, which will be totally independent of the previous basis function phi 1 of t. And this is how we are finding the basis function. That's how the basis functions are. They are totally independent of each other. And if there is some contribution with each other, you are subtracting them out of this process. So as a result, the GSO process will make all the basis functions independent of each other. There will be no contribution of one function with each other. They will be orthogonal to each other. So the successive basis functions are found by removing portions of the signals that are correlated to the previous basis functions and then normalizing the result. This procedure is repeated until all basis functions are found. So you do this process until all the basis functions are found, exhaustively doing this process, right? So if in any step the function g of t is equivalent to 0, then no new basis functions are added. That is, if in any step this g, by the way, this is gk of t, it should have been fk of t, please correct it. If in any step fk of t comes out to be 0, then in that step there is no basis function, no new basis function added into the system, right? So you only add the basis function in your signal set, in your basis signal set, when this fk of t is non-zero, right? So this procedure is repeated until all the basis functions are found, and if fk of t is equal to 0 in any step, then no new basis function is added into the basis function set. And by the way, this is written here again. The order in which you select the signals in the GSO process is arbitrary. You don't fix the order. You may select them randomly, but you need to ensure that all of them are chosen at least once, so that you check for all of these signal types and see if there's if there is any signal left to be checked in the process. All right. So that was the summary. Now it will be best understood when you see the worked out examples in the next few slides. All right. So I'll take a break here, and in the next few slides I'll show you the examples in the next session of the lecture.